For our example problem of a weak acid strong base titration, I'm going to try to keep it as similar to our example of a strong acid strong base titration as I can. I want you to be able to see the difference between these two problems. So we had 40 milliliters of HCl in our last example, and in this one we're going to use 40 milliliters of 0.1 molar acetic acid. Acetic acid is a weak acid, and we're going to titrate it with 0.1 molar sodium hydroxide. In our last example, we also used 0.1 molar of sodium hydroxide. So we would have our acetic acid in the Erlenmeyer flask, our sodium hydroxide in the burette, and we would slowly be adding our sodium hydroxide drop by drop to our acetic acid. We want to calculate the pH before we add any titrant, so that would be 0 milliliters of sodium hydroxide. Before the equivalence point, we'll choose 10 milliliters of sodium hydroxide being added. You would have to look at your actual problem to figure out how many milliliters it wants to be used. At the half equivalence point, since we have 0.1 molar acetic acid and 0.1 molar sodium hydroxide, and we started with 40 milliliters of the weak acid, it's going to take us half of the volume to get to the equivalence point. So that would mean we would have added 20 milliliters of our base. So 20 milliliters of sodium hydroxide to reach the half equivalence point. At the equivalence point, that will require the same volume of base being added as we had of acid. So that will require 40 milliliters of sodium hydroxide to neutralize all of the acid. And after the equivalence point, where we're going to be adding excess base, we'll use 60 milliliters of sodium hydroxide. These are the exact same volumes that we used in our example of a strong acid being titrated with a strong base. So just trying to keep everything consistent so you have a template that you can follow when you're doing problems. Calculate the pH at the following locations for the titration of 40 milliliters of 0.1 molar acetic acid with 0.1 molar sodium hydroxide. Number 1, before the addition of any titrant. So we said that was going to be 0 milliliters of sodium hydroxide added at that point. Our overall equation throughout the problem is going to be acetic acid reacting with sodium hydroxide to form water and sodium acetate. At this point, we haven't added any sodium hydroxide, so no neutralization reaction has occurred. All we have in our Erlenmeyer flask is our weak acid, our acetic acid. So we can write the dissociation of our weak acid. Acetic acid is going to ionize to a small extent into the hydrogen ion and its conjugate base, the acetate anion. We have done many problems calculating the pH of a weak acid solution. So initially, before you add any titrant, you're going to do a weak acid pH calculation. If you would like to, you can set up your ice table, and our initial concentration of our weak acid, we were told was 0.1 molar, so we'll plug that in to our I line. Initially, we have no dissociation occurring, we're assuming, so 0 for the hydrogen ion, 0 for the acetate anion. And when our weak acid dissociates, we don't know how much it's going to dissociate by, so we call it minus X. And then we're going to form hydrogen ion and acetate in the same amount that the acetic acid actually does dissociate. So those will both be plus X. Our equilibrium line then will be 0.1 minus X, and then X for hydrogen ion and X for acetate anion. We would next write our equilibrium expression. Ka is equal to the concentration of our products, which are hydrogen ion and acetate anion, over the concentration of our reactants, which all we have is our weak acid, acetic acid. We can look up on our acid-base ionization chart the Ka for acetic acid, which will be 1.8 times 10 to the negative fifth. We can then take our equilibrium line concentrations and plug those in to our equilibrium expression to get the pH. We're going to have to solve for the hydrogen ion concentration. So our Ka is 1.8 times 10 to the negative fifth power equals X times X in the numerator all over 0.1 in the denominator. That's because, recall, we can ignore that minus x term because our Ka is very small. This is going to usually be true for the majority of our weak acids and our weak bases. So what we end up getting when we multiply 0.1 by both sides is we get 1.8 times 10 to the negative 6 is equal to x squared. And then when we take the square root of that, we'll get x is equal to 1.34 times 10 to the negative third. And that's the molarity of our hydrogen ion. So that's our concentration of our hydrogen ion in solution. Lastly, to get at the pH then, we need to take the negative log of our hydrogen ion concentration. So negative log of 1.34 times 10 to the negative third. And that gives us an initial pH of about 2.88. So our initial pH of our strong acid was 1, whereas our initial pH of our weak acid is about 2.88. So it's much higher because it's not a strong acid. We haven't added any sodium hydroxide, so no neutralization has occurred. Your initial calculation before adding any titrant is simply the dissociation of a weak acid calculation. And since you have a weak acid, you're going to have to use an equilibrium expression. Whereas for a strong acid, we could just use stoichiometry and calculate moles. Next, we're going to calculate the pH before the equivalence point is reached. I'm going to choose 10 milliliters of sodium hydroxide being added from our burette to our Erlenmeyer flask at this point. This is the same amount that we used in the strong acid, strong base titration. Last time we jumped right into calculating moles, but first let's think about what's going on here. We have acetic acid reacting with the hydroxide ion of our strong base, and when that neutralization reaction occurs, we form water and acetate anion. Now, we don't have enough sodium hydroxide to completely neutralize all of the acetic acid at this point, so there's really not going to be any sodium hydroxide left over when we've added the 10 milliliters because every drop of hydroxide that's added is going to get reacted away with some of the acetic acid that's present in solution. So let's figure out how many moles of acetic acid we had initially and how many moles of sodium hydroxide we've added so far. So our moles of our acetic acid can be calculated by taking the molarity of our acetic acid, which is 0.1 moles per liter, and multiplying by the volume in liters. So we had 40 milliliters, so we'll multiply by 0.04 liters. That gives us 0.004 moles of our acetic acid. So initially, before any hydroxide was added, we had 0.004 moles of our acetic acid present. And then we added 10 milliliters, so let's figure out how many moles of hydroxide we added. Our concentration of hydroxide was also 0.1 moles per liter, and we added 10 milliliters or 0.01 liters. So we added 0.001 moles of hydroxide ion from our burette. So we added 0.001 moles. Water is a liquid, we'll ignore that. Now what happens is for every drop of hydroxide that you add, it's going to rip a proton off of your weak acid, and it's going to cause the concentration of the acetic acid to decrease by the amount of hydroxide that you added. And when you rip a proton off of your acetic acid, you form a mole of acetate. So it's going to cause the acetate to go up by the amount of hydroxide that you added. So initially we had no acetate present, but we're going to have some after we've added our 10 milliliters of sodium hydroxide. So our 0.004 moles of our weak acid is going to go down by the amount of hydroxide we added, which is 0.001 moles. Our hydroxide is going to go away because it's getting neutralized by our weak acid. And our acetate is going to go up, so we'll use a plus sign here, by the number of moles of hydroxide that was added. So after some of this neutralization has occurred, we're going to be left with 0.003 moles of our weak acid, acetic acid. We're going to be left with 0 moles of our hydroxide because it's been neutralized. And we've created 0.001 moles of acetate anion. So this is essentially a buffer type calculation at this point because what we have present in our flask after this partial neutralization is we have weak acid, acetic acid present, with some conjugate base, acetate anion. And we have an appreciable concentration of both of those present. And that's what you need in order to have a buffer. This is why on the titration curve, this region remains relatively constant with its pH. It doesn't change very much because even though we're adding strong base to our weak acid, every drop of strong base is creating some more of the conjugate base. So our equilibrium line tells us how many moles we have of our weak acid and our conjugate base. And notice that the number of moles of hydroxide that was added is the same as the number of moles as the acetate anion. So your hydroxide ion concentration will always equal your conjugate base concentration before the equivalence point here. Now, there is no hydroxide ion left after this partial neutralization, so this is not going to be our final equation that we want to use. This ice table was just simply to figure out how many moles of our acid and its conjugate base we have present at this point. Since all 10 milliliters of the hydroxide ion has been neutralized, all we have left after our 10 milliliters have been added is once again weak acid. So our weak acid will dissociate into the hydrogen ion and the acetate anion. So we're going to use this to set up our actual final ice table before we calculate the pH. Our initial concentration of our acetic acid can be calculated by taking the number of moles and dividing by the total volume in liters. So we calculated that the number of moles of acetic acid that were left over was 0.003 moles, and we had 40 milliliters of our weak acid in the flask initially, and we added 10 milliliters of sodium hydroxide. So our total volume at this point is 50 milliliters of acid and base that's in our flask. So we're going to divide by 0.05 liters. That gives us a concentration of our weak acid initially being 0.06 molar. So we can plug that in to our initial line for our acetic acid. And before our acetic acid actually ionizes, we want to figure out what our concentration from the partial neutralization reaction is of our anion, our conjugate base, C2H3O2-. So we had 0.001 moles of our acetate anion that were formed from the hydroxide ion being added, and that's in the same flask as the acid, so the total volume will also be 50 milliliters. So we're going to divide by 0.05 liters, and that gives us a concentration of acetate as 0.02 molar. So we can plug that in for our initial concentration of our acetate anion. Now we're assuming that this is before the dissociation of our weak acid, so our concentration of hydrogen ion is 0. This is a common ion problem. We had some acetate present from the partial neutralization with our weak acid initially. So when we get some additional formed from this dissociation, our weak acid is going to go down by -X, hydrogen ion will form by +X, and some more acetate will form by +X. At equilibrium, we're going to have 0.06 -X, X, and for our acetate, we'll have 0.02 +X. Now we can write the same equilibrium expression as we did in part number 1. Ka will equal hydrogen ion concentration times acetate anion concentration all over the concentration of our acetic acid. The Ka for acetic acid, if you look it up on your chart, is still 1.8 times 10 to the negative fifth. And we're going to plug in everything into our equilibrium expression now. We can also ignore x's that are added or subtracted because our Ka is very small, so we'll ignore minus x and plus x. We're going to have 1.8 times 10 to the negative fifth equals x for our hydrogen ion concentration, 0.02 for our acetate anion concentration, all over 0.06 for our acetic acid concentration. And we want to solve for our x, which is our hydrogen ion, so we can calculate the pH. X, or our hydrogen ion concentration, should come out to being 5.4 times 10 to the negative fifth molar. And from here, we can take the negative log of that value in order to get at the pH. So negative log of 5.4 times 10 to the minus fifth gives us a pH of about 4.27 after 10 milliliters of our sodium hydroxide have been added. Anywhere before you reach the equivalence point, you're going to end up doing a buffer calculation. You're going to end up having some amount of weak acid present with some amount of conjugate base. The amount of conjugate base present will depend directly upon how much of your strong base was added during the titration, as we did in the first part of number 2. Now, before we move on to the next part, I want to point out a shortcut that could help you with this buffer region calculation. We kind of dwindled down our last example to the Ka being equal to X, which was our hydrogen ion concentration, times our acetate anion concentration, which we calculated to be 0.02 molar, over our acetic acid concentration, which we got to be 0.06 molar. And we ended up solving for X. Now, this ratio of our conjugate base over our weak acid is actually what's important there. And both of those are in the same flask. So we ended up dividing by the total volume, which was 0.05 liters or 50 milliliters. Instead of calculating the molarity or the concentration of our weak acid and conjugate base, we could have actually just taken a shortcut and plugged in the number of moles of the acid in the base. So this setup would look like we'd have the Ka equal to X. X would still be the hydrogen ion concentration. And we would have plugged in directly. We had 0.001 moles of our acetate anion, and we had 0.003 moles of our acetic acid after that partial neutralization that we calculated from that very first ice table. Notice the ratio is the same at that spot. So in our equilibrium expression, that exact ratio didn't change, whether we divided by 0.05 liters or not. So once you get the moles actually of your weak acid and your conjugate base, since they're both in the same flask, in the same volume, you could technically skip the step of calculating their concentrations to use in the second ice table. You could jump right into plugging the number of moles into your equilibrium expression. This next part we're calling 2a, which is the half equivalence point, but it's still essentially going to be the same type of calculation we just did in the previous part because we haven't reached the equivalence point yet. So we're still doing a before the equivalence point calculation. At the half equivalence point, it would take us 20 milliliters of sodium hydroxide to reach that because we started with 40 milliliters of our weak acid. And since we have the same concentration of our base and our acid, it'll take us exactly half of the volume to neutralize half of the weak acid. So just for practice, if we set up the same overall equation that we were working on, we had our weak acid slowly being neutralized with our strong base, forming water and acetate anion. Every drop of base, we said, will end up removing a proton from our weak acid and forming some of our conjugate base. And that's going to still be true at this point. So our concentration of our weak acid is going to go down by the amount of hydroxide we add, and the concentration of our conjugate base is going to go up by the amount of hydroxide that we add. So initially, we could calculate our moles of acid and our moles of hydroxide and figure out how much they're changing by. So starting off, we had 0.004 moles of our weak acid. And when we add 20 milliliters of base, we're going to be adding 0.002 moles of hydroxide. We're going to ignore the water because it's a pure liquid. And our acid concentration is going to go down by the number of moles of hydroxide that's added. And our number of hydroxide ions are going to get reacted away with that weak acid. So those are also going to go down. Initially, we had no acetate anion, we're assuming, and it's being formed every time a mole of hydroxide removes a hydrogen ion and forms water. So we're going to have plus 0.002 moles of our acetate anion. Our equilibrium then would be 0.002 moles of acetic acid left over. No moles of hydroxide ion remain. They've all been reacted away. And we formed 0.002 moles of acetate. So at the half equivalence point, what always ends up happening is the moles of weak acid equal the moles of conjugate base. This is always going to be true at the half equivalence point. So since we have no hydroxide that remains, remember this is not going to be our equation that we use to write our equilibrium expression. All we have left is weak acid present with our conjugate base. So we're still just going to have the dissociation of a weak acid for our actual equation that is left over in our flask. So our acetate breaking up into hydrogen ion, and our acetic acid breaking up into hydrogen ion and acetate anion. Our equilibrium expression would be Ka equals H plus times C2H3O2 minus all over HC2H3O2. And just like we looked at that shortcut last time, when we actually go to plug in our numbers, we can use the moles that we just calculated above instead of calculating the molarity. So X would end up being our hydrogen ion concentration. We have 0.002 moles of our acetate anion at this point, and we have 0.002 moles of our weak acid, acetic acid. The Ka for our acetic acid is 1.8 times 10 to the negative fifth. So notice what happens at the half equivalence point when we go to calculate the pH is since the moles are the same, they end up canceling out. And X, which is our hydrogen ion concentration, ends up being equal to our Ka. In this case, the 1.8 times 10 to the negative fifth. So at the half equivalence point, this is a shorthand thing that you can use because if you understand that the moles of the weak acid and its conjugate base are the same, then the X value will always end up being equal to the Ka. And if we were to take the negative log of both sides, that means that at the half equivalence point, the pH will actually be equal to the pKa of the weak acid. So our pH can be calculated by taking the negative log of 1.8 times 10 to the negative fifth, which gives us a pH of 4.74. So a little bit higher than when we had 10 milliliters added, but not too much higher because we're in that buffering region on the titration curve at this point. Next, we're going to calculate the pH at the equivalence point. To reach the equivalence point of a titration, this is where the moles of our acid are equal to the moles of our base. So when the moles of our acetic acid is equal to the moles of our sodium hydroxide. We started with 40 milliliters of 0.1 molar acetic acid. And since we're titrating with 0.1 molar sodium hydroxide, and it has the same concentration as our acetic acid, it's also going to take us 40 milliliters of sodium hydroxide to reach the equivalence point. Just like we saw it took us 20 milliliters of sodium hydroxide to reach the half equivalence point previously. So our overall reaction that's happening is the acetic acid is reacting with sodium hydroxide in a neutralization reaction, producing water and a salt. The salt is sodium acetate. Before the equivalence point was reached, we still had acetic acid left over after some of the sodium hydroxide was neutralized. But at the equivalence point, since both of these were equal moles, we've essentially neutralized all of our acetic acid, and the hydroxide ion is neutralized as well. So all that we really have present at the equivalence point in our flask is water and sodium acetate. Those are the only two things left over now. So we have to decide what type of a salt sodium acetate is. So sodium acetate is composed of sodium cation and the acetate anion. And we previously learned that the sodium ion is neutral and it will not undergo hydrolysis, whereas the acetate anion is a weak base itself and it's going to undergo base hydrolysis. It'll be basic. So at the equivalence point, the type of problem that you want to do is a hydrolysis calculation. You want to decide what's going to be able to react with water and change the pH. So just because we've had complete neutralization and we have water and a salt present, it doesn't mean that that salt is going to be neutral. With a strong acid, strong base at the equivalence point, we did have a neutral salt that was formed and the pH was equal to 7. But here we're going to have to actually calculate the pH because we're going to have some base hydrolysis taking place with our acetate anion. So we actually have to write the equation for this hydrolysis occurring. It's going to be C2H3O2 minus acetate plus H2O because it's going to react with the water that it's in the flask with. And the base is going to accept a proton from water, forming a little bit of acetic acid. And when water loses a proton, we're left with hydroxide. So at this point, it's going to be setting up an ice table for hydrolysis just like we've done in the past. We often ignore our water and cross that off because it's a pure liquid and its concentration remains unaffected. But we need to know what our initial concentration of acetate is before this hydrolysis occurs. So we're going to have to calculate what that initial concentration is by figuring out how many moles of acetate are present at the equivalence point. Now, recall that when we did a buffer problem, every drop of sodium hydroxide that we added formed a mole of acetate anion. So we're going to have to use the sodium hydroxide to get at the moles of our acetate. So to calculate moles of acetate anion, that's going to be equal to moles of hydroxide ion. This is very important because nowhere in the problem do you see moles of acetate being thrown out at you. So to get the moles of hydroxide, we're going to take the concentration, 0.1 moles per liter, times the volume of hydroxide we've added in liters. At this point, we've added 40 milliliters of hydroxide. So we're going to multiply by 0.04 liters, and that gives us 0.004 moles of hydroxide ion. That is equal to 0.004 moles of acetate being formed, just like we saw with the buffer problems. Those two were the same amount because every drop of hydroxide formed a mole of acetate. Now, in this case, we do need to calculate the concentration. We can't use our shortcut here. So to get at our concentration of acetate, we need to take the number of moles, 0.004 moles, and divide by the total volume in our flask in liters. So we had 40 milliliters of our weak acid. We added 40 more milliliters of sodium hydroxide. At this point, we have a total of 80 milliliters in our flask. So we're going to divide by 0.08 liters at this point. This gives us an acetate ion concentration of 0.05 molar. So at the equivalence point, we have 0.05 molar acetate. We're going to plug that into the initial line of our ice table. And now it just becomes like any other weak base calculation. Before the hydrolysis occurs, we have no acetic acid no hydroxide. When acetate ion reacts with water, it's going to go down by -X. We're going to form some acetic acid and hydroxide, both by +X. The equilibrium line will be 0.05 minus X. It'll be X for acetate and X for hydroxide. So now we're going to use our equilibrium line and plug that into an equilibrium expression for our weak base. So at this point, we have a weak base reacting. So we're going to have to use a Kb value, not a Ka, since we have base hydrolysis occurring. So next for our hydrolysis reaction, we're going to want to write our equilibrium expression. We're going to have Kb equals the concentration of hydroxide ion times the concentration of acetic acid, the little bit that's formed from hydrolysis, all over the concentration of our weak base, which is acetate. We figured out that we're going to have X for our hydroxide ion, X for our acetic acid, all over our concentration that we calculated, 0.05 minus X for our acetate anion. Now, we can ignore the minus X in the denominator because the Kb value for the acetate anion off your chart is 5.6 times 10 to the -10th. So it's a very small value for the Kb, allowing us to once again ignore that minus X in the denominator. So we end up having X squared over 0.05 is equal to 5.6 times 10 to the -10th. We get X, or our hydroxide ion concentration, coming out to 5.29 times 10 to the -6th. Since we have hydroxide ion concentration, we're not going to calculate pH directly. Instead, we're first going to calculate the pOH of the solution by taking the negative log of the hydroxide ion concentration. So negative log of 5.29 times 10 to the -6 gives us a pOH of 5.28. And then the pH will be equal to 14 minus the pOH. So we'll have 14 minus 5.28, which gives us a pH of 8.72. And as we would expect, the pH at the equivalence point is greater than 7, so it's basic. This is because we had that base hydrolysis taking place. If you ever have a weak acid being titrated with a strong base, the pH at the equivalence point for that setup is always going to be greater than 7. How much greater than 7 will depend upon the Kb for that anion that's formed for the conjugate base of the weak acid. So at the equivalence point, you're always going to do a hydrolysis calculation if you have a weak acid strong base titration, or if you had a weak base being titrated with a strong acid. If you have a weak acid or a weak base thrown in anywhere, you'll always have a hydrolysis calculation at the equivalence point. Last but not least, we're going to calculate the pH for our weak acid strong base titration after the equivalence point. And just to keep it the same as our very first example with strong acid strong base, I'm going to say after 60 milliliters of sodium hydroxide have been added. So at this point, we have neutralized all of our weak acid, and we're essentially just adding excess base. Any bit of sodium hydroxide that's added beyond the 40 milliliters required to reach the equivalence point is considered excess. So even if you added 40.01 milliliters of sodium hydroxide, that would still be after the equivalence point and you would have excess base present. So this goes back to actually just being a general stoichiometry problem now, because we can figure out how many moles of excess base we have to calculate the pH. A few times throughout this example, we calculated the moles of acetic acid. Initially, we had 0.1 molar and we had 40 milliliters, so that gave us 0.004 moles of our acetic acid. And At this point, we can calculate the moles of our hydroxide ion. We have 0.1 moles per liter of our sodium hydroxide concentration, and we're adding 60 milliliters, so we're going to multiply by 0.06 liters. So that gives us 0.006 moles of hydroxide ion. Notice this time when we take the difference between our acid moles and our hydroxide moles, we're going to have leftover hydroxide. So at this point, we're going to subtract the number of moles of acid from the moles of hydroxide. So 0.006 moles of hydroxide minus 0.004 moles of our acetic acid. And that leaves us with 0.002 moles of hydroxide ion that are left over that will essentially remain unneutralized. Now, to calculate the pOH, we need to figure out the concentration of the hydroxide ions in solution. So we got the moles, 0.002 moles of hydroxide, and we need to divide by the total volume in liters. We had 40 milliliters of acid in our flask, and now we've added an additional 60 milliliters of base, so we have a total of 100 milliliters of solution in our flask. We're going to divide by, that means 0.100 liters. That gives us a hydroxide ion concentration of 0.02 molar at this point. The pOH can be calculated by taking the negative log of the hydroxide ion concentration. So we'll have negative log of 0.02, and that gives us a pOH of 1.7, and then our pH will be equal to 14 minus 1.7, the pKw minus the pOH, and that gives us a pH of 12.3 after 60 milliliters of base have been added. And notice at this point the pH is much greater than 7. So this is very basic. And we saw early on that the pH of a weak acid strong base titration after the equivalence point looks exactly like the pH curve of a strong acid being titrated with a strong base. Because once you're beyond the equivalence point, you're just adding excess base. Since there's no acid left over, the two titration curves look identical beyond the equivalence point. So this calculation is identical to the part 4 that we did for the strong acid, strong base titration. The whole exact part of this problem is the same, including the numbers and the answer, because it just comes down to the stoichiometric relationship between acid and base.